Okay, good afternoon to all. This is our fourth lecture session. So, in the previous lecture, we have mainly discussed on a single property called as density, and then what are the different ways of representing density. For example, it can be expressed in terms of specific gravity and inverse of density is specific volume. Okay. Then typically for fluids, density is a strong function of temperature and pressure. It means that if we change the temperature and pressure in a flow field, then there are high chances that density of the fluid medium can also change. Particularly for liquids, the effect of pressure is less significant in comparison to effect of temperature. On contrary, for gases, pressure effect is more pronounced in comparison to the effect of temperature on density. Okay, and we also tried to see two particular important parameters. One is coefficient of volume, coefficient of compression, and coefficient of volume expansion, which actually decides if we are having some flow field where both temperature and pressure are changing, then how changes in density are actually accounted due to the combined effect. Okay, so that is something which we have seen. Then we started one another interesting discussion that was particularly related to the speed of sound. Why this discussion on speed of sound is important? Because it helps us in determining whether we will be having whether we will be having considerable density change in a flow field or not. Okay, so typically if you recall, while we were deriving the speed of sound, we considered that sound is nothing but a weak wave, and across this weak wave we are having infinitesimally small change in the properties. Okay, and the phenomena of sound wave propagation is nothing but an isentropic process. So now typically for this sound wave we obtained the equation that c square is nothing but equal to del p by del rho at constant entropy. Now how this relation can be utilized to determine the value of speed of sound in a medium, that let's try to see. So typically for an isentropic process, you will study in your course of engineering thermodynamics that for an isentropic process I can say that P into specific volume power K equal to constant. Okay, here what is K? Here K is nothing but ratio of specific heats. Okay, so we have two types of specific heats. One is called as specific heat at constant pressure and other is called as specific heat at constant temperature. Okay, so ratio of Cp by Cv is something which is called as K. Okay, now for an isentropic process, so this equation whatever I am writing over here, this is nothing but applicable for isentropic process. So as I told you that the propagation of sound wave is nothing but an isentropic process. So for this process PV power K can be written as constant, where K is nothing but equal to ratio of specific heat Cp by Cv. Okay, so now what will be happening, I can write this P by rho power K equal to constant. From here I can simply write P is equal to C times rho power K. Now if I calculate del P by del rho at constant entropy, so this equation P equal to C rho K is applicable for isentropic process, it means it is applicable for a constant entropy process. So if I take the derivative of pressure with density, so that will be coming out to be C into K times rho power K minus 1. Okay, now I can replace this C with nothing but P by rho K. Okay, so I can replace C with P by rho K. So if I replace, then P by rho K into K into rho times K minus 1, that I will be getting. Okay, so from here this will become equal to nothing but K P by rho. Okay, so from here I can simply say that the square of speed of sound can be written as K P by rho. So in any medium, if you know the pressure of the medium, if you know the density of the medium, then and if you know the ratio of specific heats for that particular medium, then you can determine the speed of sound in that particular medium. Okay. Now, if I take the assumption of ideal gas, okay, so for ideal gas, or sometimes we also call it as a perfect gas. So for ideal gases or perfect gases, typically we have pressure is nothing but equal to rho at T. So from here I can write that P by rho for an ideal gas will become nothing but equal to RT. So I can write that square of speed of sound for an ideal gas can be equal to K at T, from where the very important relation which you might have seen earlier as well, we get that C is nothing but equal to square root of KRT. Okay, is this one clear? So we have actually determined the speed of sound in a particular medium. Now, typically, why this speed of sound is important? Because we define over here a non-dimensional parameter, which is nothing but the velocity of a flowing fluid divided by speed of sound in that particular fluid, and that non-dimensional number is called as Mach number. Okay, and depending upon the different values of Mach number, we are having different flow situations, and below a certain critical value of Mach number, we say that the changes in density of the fluid medium will be negligible. Okay, so there will not be significant changes in the density of the fluid medium, and we can assume it as nothing but a incompressible flow. Okay, so let me define over here the parameter. So as I told you, the name of the non-dimensional parameter is Mach number. Okay, it is typically given by a symbol MA. Okay, or sometimes even simply M. Okay, so Mach number is defined as velocity of flow field. Okay, so velocity of flow field is, say, V flow divided by speed of sound in that particular fluid medium. Okay, and this particular non-dimensional number gives us the different, so depending upon the speed of sound and velocity of the flow, we can have different situations. Okay, so typically a situation for which Mach number is less than 0.8, that particular flow is called as subsonic flow, where the speed of the flow is less in comparison to speed of sound in that particular fluid medium, then we call the flow as subsonic flow. Okay, on the other hand, when my Mach number is in between 0.8 to 1.2, then particularly we call the flow as nothing but transonic flow. So what is happening? This is the reason in which transition is happening from subsonic conditions to supersonic conditions. Okay, so that is why this particular regime is something which is called as transonic flow. Then we have when the Mach number of the flow is greater than equal to 1.2 but less than 5. Okay, so Mach number is greater than 1.2 but less than 5. In this region we call the flow to be hypersonic flow. So typically if you see all your aircrafts, modern day aircrafts, so these involve nothing but the hypersonic flows. Okay, so you have aircraft, so velocity of aircraft will be somehow greater than, if it is greater than the speed of sound in that particular fluid medium, then we will be calling our flow to be hypersonic flow. And sorry, I have written it wrongly, not hypersonic, this is called as supersonic flow. Please make this correction. This is not hypersonic, this is called as supersonic flow. Okay, so in typically supersonic flows, the analysis becomes more complex because we are not having normal fluid medium, but we are having the presence of some sudden changes in the properties which are associated with the occurrence of the special type of strong waves present in the flow medium, which are called as Mach waves. Okay. So typically when our Mach number is in this range, like it is far greater than 1, then we are having the occurrence of the shock wave and flow analysis becomes more challenging. And in these scenarios, there are significant changes in the density of the fluid medium, and these changes leads to significant changes in other properties as well. For example, enthalpy, internal energy, pressure, temperature, etc. Okay, so that's why this is called as supersonic flow. Then when we are having Mach number greater than equal to 5, then we call the flow to be nothing but hypersonic flow. And hypersonic flows are mostly associated with the flow of with the motion of the space vehicles, with the motion of the rockets. Okay, so if you see a rocket is moving, so typically a rocket moves at hypersonic speed. And in case of hypersonic flows, the analysis is even more complex because the fluid medium close to the surface of the solid reaches the state where temperature is greater than about 3000 Kelvin. Okay, so in that scenario, what happens basically, whatever molecules are present in the air, in the atmospheric air, these molecules gets ionized, and these molecules go through number of chemical reactions, and these changes their actually molecular structure. Okay, so this flow is then further more complex. Okay, so these are the different flows which we can categorize based on the value of the Mach number. Typically, why Mach number is important for our study? None of these flows we will be studying in this course. In this particular course, mainly we will be referring to the condition of subsonic flow, where our Mach number is less than 0.8, but even not less than 0.8, we will limit ourselves to Mach number condition of 0.3. Okay, why? Because when our Mach number is less than 0.3, then in our flow field, the corresponding changes in density are less than equal to 5%. Okay, so if in a flow field our density of the fluid is not changing by margin of more than 5%, we consider that our density, we can take the assumption of constant density, and such type of flows are called as nothing but incompressible flows. So here I am considering density to be constant, and typically I am calling my flow as incompressible. Is this point clear? And if my Mach number is greater than 0.3, then I will be having changes in density greater than 5%, and under that scenario, I cannot accurately take the assumption of constant density. That's why we have to consider that density in these conditions is variable, and when density is variable, it is changing at different locations of the flow field, then we do call the total flow regime as nothing but compressible flow, and we have to go for more advanced calculations where in our continuity, momentum and all other equations, we have to account for the variations in density. Is this point clear? So for Mach number less than 0.3, our density will be constant, and for Mach number greater than 0.3, density will not be exactly constant, but changes in density are less than 5%. So that can be considered as the condition of a constant density with reasonable accuracy. Okay. On contrary, when my density change is greater than 5%, then if I keep on solving the incompressible equations, then amount of errors coming into my analysis will be significant. So that is the reason we have to account for the compressible effects. Okay, is this point clear? So this is the discussion regarding density, which is an important property, and we have seen how density actually helps us, density and the associated parameters such as particularly over here Mach number is helping us in deciding whether we can take the assumption of incompressible flow or compressible flow. Okay. in this particular course of fluid mechanics, we will be only dealing with the regime where Mach number is less than 0.3. It means our constant density assumption is applicable. Okay. So similar to density and specific volume, there are other properties. For example, one of the property is pressure. Okay. So can you tell me what is the fundamental definition of pressure? Force per unit area. So more precisely we can say that in an hydrostatic situation, the normal compressive stress that is acting on the fluid element, that we can call as nothing but the pressure. Okay, so what I am trying to say over here, I am saying that three keywords. One is hydrostatic situation. So because if situation is hydrostatic, then shear stress will be 0. Okay, so in that situation, whatever the normal compressive stress, that is acting on a fluid element, that we are calling as nothing but our pressure. Okay, and typically pressure is nothing but equal to force per unit area. Okay, now likewise we have defined in terms of density that if we keep on decreasing the volume, then we may find some situation where assumption of continuum is not applicable. So similarly, if you keep on decreasing the surface area for calculation of the pressure, then also you may find some situation where continuum approximation is not applicable. So if we have to define the pressure in a more generic sense, then I can write that pressure is equal to limit delta A approaches to delta A star into delta P by delta A, where delta A star is nothing but the limit of control surface where continuum is applicable. Is this point clear? If I take any surface, control surface, which is having area less than delta A, less than delta A star, then whatever the pressure I will be getting, that will not be correctly reflecting the average pressure, whatever we conceive from the fluids in continuum. Okay. So if you are taking the assumption of continuum, then pressure gives us a benefit that if I have say a closed chamber, and in this closed chamber if I have say large number of gas molecules present, okay, so of course what will be happening, these molecules will keep on rotating here and there, and the molecules which are in close contact with this solid surface, these will transfer some momentum to this solid surface. Okay, the molecules will keep on striking the walls of the solid surface. So that is something from the molecular approach you can say as the origin of the pressure. Okay, so the beauty of the pressure at continuum level is that even if you measure the pressure at this location, any location, if you put the pressure gauge, okay, it will give you the same value of pressure. Okay, for example, if this is the room, in this room if you put a pressure gauge on this right wall, or if you put a pressure gauge on left wall, in both the sides you will be finding that your gauge is giving a value of 1 atmospheric pressure. Okay, so that is something when we are looking the things at macroscopic level, by considering the assumption of continuum true in our system, we will be finding that whatever we will be conceiving, the property which we will be conceiving at the macroscopic level, though it is average sum of molecules, but we need not to account for the individual molecular analysis for determining this property. Okay, now when we study the pressure, so as you have seen, sorry, I have written this wrongly, it should be delta F by delta A. Now you can clearly see that it is the ratio of force per unit area. So in terms of SI units, its unit will be in SI system Newton per meter square, and Newton per meter square is typically called as Pascal. So 1 Pascal is nothing but equal to 1 Newton per unit meter square. Okay. Now in our analysis of fluid flow, pressure will play a significant role, that we will try to see in module 2 as well. So right now just I am introducing you to this property. Along with pressure, one very important associated parameter is, which is called as vapor pressure. So can you tell me what is vapor pressure? What do you mean by vapor pressure?
When over a free surface of a liquid, there is some equilibrium between the gas phase and the liquid phase. The pressure of the gas molecules exerts on the free surface, we call that vapor.
Yes, correct. So very precise definition. So whenever we define the vapor pressure, so say you are having liquid and you are having the vapor medium of the same liquid. Okay, so when vapor medium of the liquid and a liquid both are in equilibrium with each other. So what is the meaning of equilibrium? The meaning is, if any liquid at that time evaporates and gets converted into vapor, the vapor molecules has to condense into liquid in order to maintain the same situation. Okay, so this type of situation when we are having, so corresponding to this situation, whatever the pressure these vapor molecules are applying on liquid surface, that we call as vapor pressure. Okay, so let me represent it over here. Say I have a container, and in this container here I am having this free surface which is formed by the liquid under the presence of gravitational field. Okay, now this container is open from the top. Now here what I will be having? Here I will be having closely spaced molecules. So these are nothing but the molecules of the liquid. Okay, on above this surface, say here I am having the molecules of vapor. So this is vapor of the same fluid. Now I am not talking about any other pressure. For example, if you take this container, you can assume that outside container there is air, and air is also having moisture. I am not talking about that moisture present in the air. I am simply talking about only the pure water vapor molecules. And here also I am talking about the liquid water molecules. Okay, so please let me once again emphasize this. The point is, whenever I am trying to determine this vapor pressure, I am not considering that I have other gases also present over here, but I am only considering the pressure which is acting only because of the vapor. Okay, so when I have this situation, and if any liquid is getting converted into vapor, say from here this molecule is going into vapor. So any molecule from the vapor it has to enter into the liquid, then only we will be calling the state of equilibrium. Okay, otherwise what will be happening? If say it is not in equilibrium, then it may happen that liquid molecules will keep on entering into the vapor, and we will be getting that number of vapor molecules are keep on increasing, and if number of vapor molecules are keep on increasing, then they will keep on increasing the value of the pressure. Okay, so for defining a fixed value of vapor pressure at any given state, what should be there? There should be equilibrium in between the liquid and the vapor. Okay, and what do we mean by equilibrium? That just now I explained, that if any molecule of liquid is entering into vapor, converting into vapor, then one vapor molecule has also to be entered into the liquid in order to maintain the balance between them. Okay, so when this type of equilibrium is existing, and whatever the pressure these vapor molecules are exerting on this liquid, that particular pressure we call as nothing but our vapor pressure. Okay, so typically how vapor pressure can be determined? What it is representing? It is representing the equilibrium between liquid and vapor state. Okay, and it means liquid and vapor of a substance are simultaneously present in this situation. Okay, so when liquid and vapor of a substance are simultaneously present in a system, what will happen at this scenario? At this scenario, the pressure and temperature are dependent on each other. For example, how you can understand this? Can you tell me what is the boiling point of water? 100 degrees Celsius. Is there any other parameter linked to this? at atmospheric pressure. Okay, 100 degree Celsius temperature is boiling point of water only at 1 atmospheric pressure condition. But if atmospheric pressure condition changes, then boiling point of water also changes. Okay, so that is the simple principle we employ in our pressure cookers. What we do in pressure cookers? We maintain the pressure inside pressure cooker somewhere in the range of 2 to 3 bar. So when we maintain in the range of 2 to 3 bar, then its boiling temperature of the water goes to about 120 or 130 degrees Celsius. Okay, so that way we can keep adding the heat to the liquid without it is converting into complete vapor at 100 degrees Celsius. So now it will convert into vapor at say 120 or 130 degrees Celsius. So whenever the mixture of two phases of a substance is present, corresponding to that, whatever temperature and pressure we are having, these are nothing but interlinked to each other. Okay. So now this, the help of this concept we will take to define vapor pressure at this point. Let's consider that this liquid and vapor mixture which I am talking about is present at 20 degrees Celsius. So if it is present at 20 degrees Celsius, then what will be happening? 20 degrees Celsius is my temperature, and of course corresponding to this 20 degrees Celsius there will be some saturation pressure of water at which only the mixture of liquid and vapor will be existing. Okay, because if you take 20 degrees Celsius and 1 atmospheric pressure, then liquid vapor mixture will not be existing. Okay, so corresponding to this, whatever saturation pressure is there, that is something which is remarked as nothing but the vapor pressure. Is this point clear? So if we are at given temperature, corresponding to that given temperature, whatever the saturation pressure of the vapor, so saturation pressure mentions that the pressure, combination of pressure and temperature at which mixture can coexist in equilibrium. Okay, is this point clear? As in case of pressure, we have seen that if we increase the pressure, then temperature, saturation temperature is increasing, means boiling temperature is increasing. Similarly, if we increase the temperature, then vapor pressure, or in other words, the corresponding saturation pressure will also keep on increasing. Is this point clear? Now, why this is important in fluid mechanics, let me explain to you. Okay, so the simple idea is that if you have this container and it is in equilibrium, okay, so if this container is in equilibrium, then if you put a pressure gauge over here, so that pressure gauge, if these are in equilibrium, then whatever the pressure gauge will give you the pressure, that will be nothing but equal to this P vapor or saturation pressure. But for that, these two must be in equilibrium. Okay. So here one important point is, if you measure the pressure at this location, say location number 1, or if you measure at this location, which I have marked location number 2, at both the points we will get the same value of the pressure. Okay, but if I go more deeper inside, then value of pressure at location number 3, then value of pressure will not be equal to vapor pressure, because then along with the vapor pressure, the effect of gravity has to also be accounted as hydrostatic pressure. Okay, so that is why when we are measuring the vapor pressure, we can either measure in the vapor medium or we can measure even in liquid medium, but we have to measure in liquid medium very close to the interface. Fine? Is this point clear? Okay. Now another important point, I told you that if I have temperature equal to 20 degrees Celsius, so corresponding to that, whatever saturation pressure is there, that I am calling as vapor pressure. Now can you tell me what is the difference between vapor pressure and partial pressure? Are these two different or same? If different, then what is the difference? First, when does the concept of partial pressure comes? Mixture of multiple components. For example, if I talk about atmospheric air, so atmospheric air contains oxygen, nitrogen, carbon dioxide, argon and many other gases in small quantities. Along with that, it also contains the water vapor. So typically we call moisture. Okay, so it contains water also in the vapor form. So all these are nothing but forming a pressure of 1 atm. But this 1 atm pressure is formed by the mixture of multiple components. Okay, so the contribution of individual component in this total pressure is something which is called as the partial pressure of each component. Okay, so for example, if you talk about moisture present in air, moisture in atmospheric air. So when you are talking about the moisture present in atmospheric air, whatever the pressure that moisture is contributing in the atmospheric pressure, you will be calling that nothing but the partial pressure of water vapor. Is this point clear? Is this point clear what I am telling? So I will be calling it as nothing but the partial pressure of the water vapor. Now how it is different than vapor pressure, then let me explain. So if I have moisture present in the air, but air is not fully saturated, okay, it means that I have liquid molecules here, a free surface, okay, and then here I am having atmospheric air. So when I am talking about the atmospheric air, I am now drawing, if you see, I am drawing the molecules with different colors. Why I am drawing with different color? Because it is mixture of multiple gases. Say, so these are the individual vapor mediums present. Okay. Now, in these individual vapor mediums, you will be finding that, say, these blue colored molecules are nothing but of water vapor. Okay. So what you will be finding, if you put a bucket in open space, what happens? Slowly that water level keeps on decreasing unless the bucket is completely empty. Okay. So what happens basically in this situation, when I was defining the equilibrium, then what I told, that if any liquid molecule is going into vapor, then from vapor also one molecule has entered into the liquid. But in this situation, if I consider that in a mixture of air is not having enough water molecules to maintain or to ensure the equilibrium in between water vapor and the liquid, then what will happening, from here some liquid molecules can enter into this vapor medium. So if liquid molecules are entering into the vapor medium, so ultimately the content of water vapor molecules is increasing. So these water vapor molecules will keep on increasing their pressure. So it means partial pressure of the water vapor molecules will keep on increasing. Is this point clear? Okay. Liquid molecules are converting into vapor, and air is having tendency to hold more and more water molecules. So if air is having tendency, it is not yet saturated to the maximum limit. Then air will keep on handling, and as air is keep on handling the water, more and more water vapor molecules, then their partial pressure will keep on increasing. Okay. So the very first conclusion which I can make from here is that P partial will be less than P vapor. Is this one clear? At a given temperature, partial pressure will be less than vapor pressure if these molecules are not in equilibrium. But say we reach the state when these molecules has become in equilibrium with the liquid phase. In that scenario, I will be finding that whatever the partial pressure these vapor molecules are exerting, that will be equal to nothing but the vapor pressure. Okay, is this one clear? So from here, one important conclusion we can make is that partial pressure will always be less than or equal to vapor pressure. Okay, because once you have established the equilibrium in between the water vapor and the liquid molecules, after that your vapor cannot take more liquid. Even if some liquid molecule is getting converted into water, then what will be happening? Then also one vapor molecule will get shifted into the liquid side. So total balance in the vapor will be removed. Okay. So that is why partial pressure will always be less than equal to vapor pressure. Okay. And this is the reason you will be finding, particularly during rainy season, there is lots of moisture or lots of water molecules are present in the atmospheric air. So its relative humidity is very high. So relative humidity is another parameter we will not discuss in detail, but it typically represents whether the air is saturated or not. Okay. So when air is saturated, even if I keep the water bucket, we will be finding that water bucket will never get empty. Okay. So if I put a water bucket in complete atmosphere of saturated air, saturated air means the air is containing the maximum amount of water molecules which it can hold at the given conditions. Okay. So corresponding to that situation, we will be finding that the water is, or the liquid is actually not getting evaporated. Okay, so this is the reason you will be finding, even if you are having a sunny warm day, but if you are having more humidity present in the air, okay, if air is having more moisture, it will take more time for the clothes to dry. Okay, is this point clear? Now why this concept is that much important? Because we just now found that if partial pressure is becoming equal to vapor pressure, then there will not be any evaporation. But if partial pressure is less than the vapor pressure, then there will be evaporation. Okay. So typically in fluid mechanics, we use a number of devices. For example, for pumping water at your home, what you do? You use a pump. So what does pump do? Pump creates negative pressure at the suction point, so that from the tank, which is at atmospheric pressure, water can enter into the pump, and then it imparts certain energy to that water so that it can actually lift it through certain height. Okay. So one important point is here, that at the suction point of the pump, say if I consider that this is my pump and this is its suction side. So at the suction side of the pump, what I will be getting? My pressure will be less than the atmospheric pressure. If for given temperature condition, my pressure P has become less than the vapor pressure, then what will be happening? Here itself some liquid molecules will get converted into vapor. Is this one clear? So here I will be having the formation of some vapor molecules. Okay, and these vapor molecules, what these will do? These will form a vapor bubble at the suction side. Okay, and when this vapor bubble will move with the liquid and it reaches the high pressure side of this impeller, then we will be finding that in the high pressure side, this vapor bubble will collapse and it will create some disturbances and pressure waves, which will lead to the erosion of the impeller blade surface. Okay, so the phenomena of this vapor bubble formation is something which is called as cavitation. Is this one clear? At a given temperature, if my pressure of the medium is less than the vapor pressure, okay, then my liquid molecules will get converted into vapor. These will be forming a pocket of vapor medium. Okay, that particular vapor bubble, the phenomena of conversion from liquid to vapor is called as cavitation. Okay, and cavitation is having many negative effects on the performance as well as the uh, life of the hydraulic machines. Okay, is this one clear? Because when these small bubbles reaches the high pressure zone, these collapses and creates the pressure waves which can erode the material from the surface, as well as this decreases the efficiency. Okay, so that is why this is not actually desired. So whenever we design any fluid, any this hydraulic device, we try to consider that our vapor pressure should be greater than the, sorry, our pressure should be equal to or greater than the vapor pressure. Okay, because if that situation is satisfied, then there will not be any transformation of the molecules from liquid state to the vapor state. Okay, is there any doubt up to this point? Okay, next is our parameter, important parameter which we also measure, temperature. So temperature, just I am discussing over here, but in this subject of fluid mechanics, apart from just defining the state of the medium, in order to determine other properties, we will not be using any other application of the temperature. Okay, so basically whatever the kinetic energy of the molecules is there, so corresponding to that, whatever effect we perceive, that is called as the temperature. Okay, and temperature nothing but it helps us in determining the degree of hotness and coldness of any object. Okay, and if we have the difference of temperature in any medium present, then we will be finding there will be flow of energy from high temperature to low temperature, and that flow of energy is typically called as heat energy. Okay, so that you will study in more detail in the subject of thermodynamics. And temperature is having, particularly in SI units, the common unit is degree Celsius. However, in absolute scale, its unit is Kelvin. And more details about temperature and its associated scales we will be finding in the subject of thermodynamics. Okay. After temperature, one more property I defined, and that was nothing but internal energy. So can you tell me what do we mean by internal energy? It is given by symbol, specific internal energy is given by symbol small u. So what do we mean by internal energy? So if you see all the molecules in a fluid medium, these are not at any fixed positions. Okay, these are not stationary. So these molecules are undergoing certain different processes. For example, molecules are translating from this one point to other point. So these are having translational kinetic energy of individual molecules. Then some of the molecules are undergoing the rotation. Say if I have molecular structure something like this. Okay, and if this molecule rotates something like this, so this type of molecule will create, about this axis of rotation, it will create some rotational kinetic energy. Okay, then when two molecules are coming close to each other, they are having some intermolecular forces. For example, if very close to each other, then they will repel. If far from each other, then they will attract. Okay, molecules, within a molecule, if we see, there are intramolecular interactions. So it means if this is oxygen atom, these are hydrogen atoms. So these are actually joined together, connected to this each other. Okay, so these are having some bond energies associated. Okay, so all these are nothing but called as the microscopic forms of energies. So whatever the microscopic forms of energies present within a molecule at any given thermodynamic state, this is called as nothing but the internal energy. Okay, so and internal energy is nothing but a strong function of thermodynamic state. Because if you have air now at 20 degrees Celsius, and if you take the same air at 100 degrees Celsius, at 100 degrees Celsius you will be finding that air molecules are having more motions. Okay, so their translational kinetic energies, rotational kinetic energies will be different in comparison to the values which are at 20 degrees Celsius. Okay, so that is the reason that all the microscopic forms of the energy, so this is nothing but details you will study in thermodynamics. So all microscopic forms of energy which are possessed by a fluid medium at any given thermodynamic state, at any given temperature and pressure, this is called as the internal. Okay, so if I have to determine the total energy of a substance, then I have to include the microscopic energies plus macroscopic energies. So microscopic means internal energy plus macroscopic energies typically we are having in the form of kinetic energies and potential energies. So if whole medium is moving and creating a bulk motion at some velocity v, then we will be having half mv square as its kinetic energy, and if it is say at certain height, then the reference level, then we will be having certain potential energy. Okay, then we defined one property, enthalpy. Of course, the details of enthalpy once again you will study in the subject of thermodynamics, but enthalpy is typically given as internal energy plus flow work. Okay, so when you are having a flowing fluid medium, so that flowing fluid stream, in addition to its internal energy, it carries some more energy that is typically called as, this product of pressure into specific volume is typically called as flow work or flow energy. So when flow energy is added to internal energy, then we call the property as enthalpy. Okay, and then we had two other important properties. One is called as, these are specific heats. So one is called as specific heat at constant pressure Cp, and other is called as specific heat at constant volume Cv. Okay, so Cp and Cv also you know the fundamental definitions, and once again the more details you will study in the subject of thermodynamics. Okay, so now, but we should know about these properties. Typically, as I told you, in our this subject of fluid mechanics, mostly we will not be talking about all these different properties. Rather, we will mainly talk about the transport properties. Okay, so one very important property which is associated with the fluid flow as transport property, that is called as viscosity. Okay, now viscosity is given by a symbol mu. Now can you tell me how to define viscosity? Can anyone give me the definition of the fluid viscosity? You have studied it already. Resistance offered by fluid to what? To motion. Okay. Yes, so basically the principle is that when fluid flows, so the different layers of the fluid flow create some internal resistive forces. Okay, so in a broad sense we can say that the quantitative measure of the resistance of fluid to flow is something which is nothing but a viscosity. Okay, so in a broader sense what I can say that quantitative measure of internal resistance of fluid layers to its flow is something which is called as viscosity. Okay, now slowly we will study the concept of viscosity. So first what we will do, let's consider that we have a flow field where some fluid medium is actually flowing. Okay, here fluid medium is flowing, and in this flow field what we have done, we have put two plates over here, such that this is my one plate over here and this is another plate over here. Okay, so these two plates are put with very close spacing between each other. So say these are having spacing of dy between each other. So infinitesimally small spacing. Okay, now this bottom plate is fixed and top plate is subjected to some force, say df, corresponding to which we are getting some velocity du in the right direction. Okay. Now what will be happening, as previously also I have talked about one very important condition, which is called as no slip condition. Okay, so what does no slip condition does? What is the role of no slip condition? Yes, so basically what does this no slip condition does? It creates a condition where velocity of the fluid medium becomes identical to that of the velocity of the surface with which it is interacting. Okay, so it can be any other fluid surface or it can be any other solid surface. Okay, for example, if I take a solid surface, say this solid surface is at rest. Now what will happen? At macroscopic level this surface seems very smooth to us. Okay, but if you see at microscopic level, this surface will have lots of surface irregularities. Okay, and due to these surface irregularities, what will be happening? Whatever the fluid is flowing above this, that particular fluid will get entrapped in between these surface irregularities. Okay, or in other sense I can say that the molecules of this solid will have some molecular interactions with the molecules of the liquid. So typically molecules are having two types of interactions. One is adhesive and cohesive. Okay, so the molecular interactions which are within the same set of molecules, these are called as cohesive interactions, and the molecular interactions which are between different set of molecules, these are called as adhesive interactions. Okay, so here more than the molecular interactions, the idea is that if you see this surface from microscopic level, it will be having lots of irregularities, and because of these irregularities, some portions or a very thin layer of the liquid will be just adhering to this solid surface. So because of this adherence, what it will do, if we say that flow is flowing parallel to the surface, then these fluid molecules actually cannot move in this tangential direction. Okay, so as these cannot move in tangential direction, so we can say that the velocity of fluid over here is equal to velocity of the solid, which is nothing but equal to 0. Okay, now if I say this solid is also moving with some velocity of solid, then what will be happening? Whatever the molecules which are trapped in between these irregular zones, these molecules will also keep on traveling with the solid. So that is the reason we say that velocity of fluid is nothing but equal to velocity of solid, and when solid is at rest, then it is equal to, when solid is at rest, then it is nothing but equal to 0. Okay, now there is a very clear definition that no slip condition, what it is doing, it is creating only the tangential velocity which is parallel to surface, it is making that 0. Okay, it is not giving any information about normal component of velocity, what is happening to the component of velocity which is normal to the surface, because I am talking about this direction. So when I am talking about this direction, I am only referring to the tangential velocity. Okay, but in a flow field, fluid can also have normal velocity as well. Okay, so in case of normal velocity, if this solid wall is a perfect solid, it is not porous, then nothing can penetrate through this solid wall. So velocity of fluid in normal direction will be 0 when I am having impermeable wall, impermeable surface. Okay, is this point clear? So whenever we are talking about no slip condition, only we are referring to the tangential velocity. We are not talking about the normal velocity. Normal velocity will come into picture depending upon the characteristics of the surface. If surface can pass fluid layer through it, then we will be calling it as a permeable boundary. So then there will be some normal component of velocity. But if surface cannot pass the fluid through it, then we will be calling impermeable velocity, and normal to the surface velocity will be 0. Okay, now I will stop, and we will see this concept once again in more detail in the next lecture.